Good morning, students. Welcome to Bindu Dhadwal chemistry lessons. We are doing chemical properties of aldehydes and ketones. Let us continue. The reaction that we will be doing is reaction with phosphorus pentachloride with PCl5. The compounds containing carbonyl group will react in such a way that PCl3 combines with oxygen forming POCl3 and two chlorines get attached here to form a geminal dihalide. For example, acetaldehyde will react to form 1,1-dichloroethane along with POCl3. Next is oxidation reactions. Oxidation of aldehydes and ketones. Aldehydes differ from ketones in the oxidation reactions. They can be easily oxidized with ordinary oxidizing agents like nitric acid, potassium permanganate, potassium dichromate, and they form carboxylic acids with the same number of carbon atoms as the aldehyde. The reason for easy oxidation of aldehyde is the presence of a hydrogen atom on the carbonyl group, which can be converted into OH without undergoing any cleavage. On the other hand, ketones are not easily oxidized. Under drastic conditions, that is with powerful oxidizing agents such as concentrated nitric acid, acidified potassium permanganate or acidified potassium dichromate at elevated temperatures, ketones will undergo cleavage of carbon-carbon bonds to form a mixture of acids. Carboxylic acid that is formed contains less carbon atoms than the original ketone. So what we see is that when the ketones are unsymmetrical ketones, in that case the cleavage occurs in such a way that the keto group stays preferentially with the smaller alkyl group. This is known as Popov's rule. This was symmetrical ketone. When this breaks up, acid of one carbon and another acid of two carbons will be formed, formic acid and acetic acid. But in case of unsymmetrical ketones, the bond can break in two ways. One is bond is broken from this end, and the other is from this end. Will form major products because the keto group, according to Popov's rule, will prefer to stay with the smaller alkyl group. Option will be the major products, and propanoic acid and acetic acid will be formed. And on the other hand, breaking from here resulting in butanoic acid and formic acid, the products will be in lesser amounts. So according to Popov's rule, the keto group stays preferentially with the smaller alkyl group. Thus, oxidation reactions can be used to distinguish between aldehydes and ketones. Aldehydes will form acids with the same number of carbon atoms. Ketones will form acids with carbon atoms lesser than what were there in the ketones. The basis of this test is that aldehydes are very readily oxidized, not only by strong oxidizing agents, but also by weak oxidizing agents like Tollens reagent, Fehling solution, Benedict solution, etc. Under these conditions, with these reagents, ketones cannot be oxidized. So with Tollens reagent, aldehydes will be oxidized to their respective carboxylate ion. Tollens reagent is ammoniacal solution of silver nitrate and is prepared by adding ammonium hydroxide to silver nitrate so that the gray precipitates of silver oxide formed will just dissolve. So when they just dissolve, they form diamine silver hydroxide, which is Tollens reagent. So when an aldehyde is heated with this Tollens reagent, the aldehyde will reduce tolerance reagent to silver, and a silver mirror will be formed. We in a test tube we have put all aldehyde and then we add tolerance reagent, and what we see is that tolerance reagent is reduced and the silver ions are reduced as silver metal, and a mirror is formed on the outer walls of the test tube, and so this test is known as silver mirror test. So tolerance reagent is reduced to silver, whereas the aldehyde is oxidized to carboxylate ions with the same number of carbon atoms. So because a mirror is formed, this reaction is also known as silver mirror test. The mirror formation indicates the presence of aldehyde group in the molecule. Both aliphatic and aromatic reduce tolerance reagent, and ketones do not give this test. Then Fehling solution also is reduced by aldehydes but not by ketones. So Fehling solution is actually a mixture of two solutions in equal amount. Fehling solution A, which is aqueous solution of copper sulfate, and Fehling solution B, which is alkaline solution of sodium potassium tartarate, also known as Rochelle's salt. So the two solutions are mixed in equal amounts before carrying out the test. And when we add the mixture of these two solutions to aldehyde and heat it, a reddish brown precipitate of cuprous oxide is formed. So the Fehling solution contains cupric ions and hydroxide ions. Aldehyde will reduce it to cuprous ions, cuprous oxide, which forms red-brown precipitate. The presence of red-brown precipitates indicates the presence of aldehyde. The aldehyde itself gets oxidized to carboxylate ions in this reaction. So acetaldehyde will get converted to acetic ions, whereas cupric ions get converted to red-brown precipitates of cuprous oxide. In the Fehling solution, this test is given by aliphatic aldehydes only. Aromatic aldehydes do not respond to Fehling solution. They respond to tolerance reagent but not to Fehling solution. Then Benedict solution is an alkaline solution of cupric Cu2 plus ions complexed with citrate ions, whereas Fehling solution was with tartrate ions. This is with citrate ions. It reacts in the same way as the Fehling solution, that is, it also gives reddish brown precipitates of cuprous oxide. Then oxidation with sodium hypohalide. This is the second method. Aldehydes and ketones having at least one methyl group linked to the carbonyl group, that is methyl ketones or acetaldehyde, are easily oxidized by excess of halogens in presence of alkali. Halogen can be chlorine or bromine or iodine, and alkali can be NaOH. Or this acetaldehyde or methyl ketone can also be oxidized with sodium hypohalide. It can be NaOCl, NaOBr or NaOI to form haloform. The haloform can be chloroform CHCl3 or bromoform CHBr3 or iodoform. For example, this aldehyde contains alpha methyl group, the carbon with functional group. The carbon next to it is the alpha carbon, and if the alpha position carbon is a methyl group, then it will react with iodine in the presence of alkali to first get converted to triiodoacetaldehyde. Along with it, HI is formed, and this triiodoacetaldehyde will react with NaOH, take the H of NaOH and combine the CI3 of aldehyde will combine with this H to form CHI3, which is iodoform. Yellow colored precipitates of iodoform are formed. If they are formed, then that means that it is a methyl aldehyde or ketone. So it was a 2-carbon compound, so acid salt of 1 carbon will be formed. Sodium formate will be formed. Similarly, acetone can form iodoform with NaOH plus I2. Haloform reactions can thus be used to distinguish methyl ketones from those ketones which do not contain alpha methyl group. Iodoform test helps to distinguish between carbonyl compounds like methanol and ethanol. Ethanol will give iodoform, whereas methanol will not give. Similarly, ethanol and propanol will not give iodoform test, ethanol will give. Then pentane 2-one will give iodoform, whereas pentane 3-one will not give. Benzoacetophenone will give iodoform, will give positive iodoform test, whereas benzophenone will not give. And benzaldehyde will not give iodoform test, whereas acetophenone will give iodoform test. This iodoform test can also be used to distinguish the 2 types of alcohols. For example, ethanol will give iodoform test, methanol will not give. Ethanol will give, propanol will not give, because it does not contain a CH3 group at alpha position. At alpha position we have CH2. Similarly, propane 2-ol will give, but propane 1-ol will not give iodoform test. Then butane 2-ol will give iodoform test, but butane 1-ol will not give iodoform test. So this was oxidation reactions of aldehydes and ketones. Next is reduction of aldehydes and ketones. So we can reduce aldehydes and ketones to alcohols. We can also reduce aldehydes and ketones to alkanes, and we can reduce aldehydes and ketones to pinacols. To alcohols, we can do by catalytic hydrogenation or with lithium aluminum hydride and sodium borohydride. We can reduce aldehydes and ketones to alkanes by zinc amalgam and hydrogen chloride. Then this is Clementine reduction. By hydrazine and potassium hydroxide, this type of reduction is Wolff-Kishner reduction. And with hydrogen iodide and red phosphorus also, we can reduce aldehydes and ketones to alkanes. And for converting them to pinacols, we treat ketones with magnesium amalgam and water. They are converted, biomolecular reduction occurs, and they are converted to symmetrical diols, which are also known as pinacols. So let's do the first type of reduction to alcohols. Aldehydes and ketones on catalytic hydrogenation in presence of nickel, platinum or palladium or lithium aluminum hydride or sodium borohydride can be reduced to alcohols. Aldehydes will get converted to primary alcohols, ketones will get converted to secondary alcohols, and benzaldehyde to benzyl alcohol. So the bond breaks, one hydrogen gets added to carbon, another to oxygen, and as a result alcohol is formed. Lithium aluminum hydride is a more powerful reducing agent than sodium borohydride. Lithium aluminum hydride can reduce aldehydes, ketones, acid chloride, amines, nitriles, esters, nitrocompounds, etc. Whereas sodium borohydride can reduce aldehyde, ketones, acid chlorides and alkyl halides. So if we have a compound which has a carbonyl group as well as an ester group, sodium borohydride will only reduce the carbonyl group. So this gets converted to hydroxy group, whereas ester remains intact. But lithium aluminum hydride will reduce carbonyl group to OH group, and also it will reduce ester part also. This is converted to alcohol, and this portion is also converted to alcohol. So lithium aluminum hydride is stronger reducing agent than sodium borohydride. Then lithium aluminum hydride and sodium borohydride will not reduce the isolated double bond or the double bonds of benzene ring. For example, this compound, when reduced with lithium aluminum hydride, only this portion is reduced, hydrogen is added here, whereas double bond remains there. Similarly, sodium borohydride also does not touch these bonds, only this is reduced. However, in case of alpha beta unsaturated aldehydes and ketones, lithium aluminum hydride will reduce only carbonyl group, but sodium borohydride will reduce carbon-carbon double bond also. So let's check it out. So this is a compound, it contains a carbonyl group and a double bond. Lithium aluminum hydride will only reduce this portion, double bond remains there, and so we get but 2ene 1-ol, whereas sodium borohydride will reduce this as well as this, so we get butanol. It also forms this compound where a double bond is left intact, but this product is formed in greater amounts than this product where it's reducing the double bond. So sodium borohydride will form both kind of products, one where it's reducing double bond, carbon-carbon double bond along with carbonyl group, one where it is not reducing. Where it is not reducing is formed in greater amounts. But on catalytic hydrogenation, this is also reduced along with carbonyl group. In order to reduce aldehydes or ketones selectively without reducing carbon-carbon double bond, we can use this reagent 9-BBN. It's a hydroborane. If we do catalytic hydrogenation, this is reduced, but if we use 9-BBN, this is left intact. Only carbonyl group is reduced to alcoholic group, CH3, CH double bond, CH, CH2, OH. Ketones can also be reduced to corresponding secondary alcohols by heating them with aluminium isopropoxide in isopropyl alcohol. So ketone reacting with aluminium isopropoxide in isopropyl alcohol, this is reduced, H and H comes here, so RCH ROH is formed. This reaction is called Meerwein-Pondorf-Verley reduction reaction, and in this reaction a hydride from isopropyl alcohol is added to the carbonyl carbon of ketones and reduction is carried out. Next is reduction to hydrocarbons. So aldehydes and ketones can be reduced to corresponding hydrocarbons by 3 methods. Let's do them. On reduction, in general, this carbonyl group, oxygen will be taken away and 2 hydrogens will be added and hydrocarbon will be formed. So if we used zinc amalgam and concentrated hydrochloric acid, the reaction is known as Clementine reduction. The alkane with the same number of carbon atoms is formed. 4 hydrogens, 2 will be used in making water and 2 hydrogens to form alkene. For example, ethanol will form ethane, acetone will form propane, and acetophenone will form ethyl benzene. The reaction is called Clementine reduction with zinc, mercury, and hydrogen chloride. Then we can also reduce it into hydrocarbon with a basic solution of hydrazine. Then it is known as Wolff-Kishner reduction reaction. In this method, aldehyde or ketone is first heated with hydrazine, water is taken out and hydrazone is formed. Then in a basic solution at 453 to 473 Kelvin temperature in glycol solvent, the nitrogen will be taken out and alkene with the same number of carbon atoms will be formed, and the reaction is known as Wolff-Kishner reduction reaction. For example, when we react acetaldehyde with hydrazine and then KOH, first hydrazone of acetaldehyde is formed, and then as ethane is formed and nitrogen is given out. Then third method is reduction with hydrogen iodide in presence of red phosphorus. So with hydrogen iodide, this aldehyde is reduced to alkane and iodine is formed in the presence of red phosphorus. Similarly, acetaldehyde will be reduced to ethane and acetone will be reduced to propane. Reduction to pinacols, the last method, this is biomolecular reduction reaction. Two molecules of ketone will get added up by magnesium, amalgam and then water. Reduction occurs, the hydrogens help in binding them up. Oxygen gets converted to OH group. So CH3C, CH3 group is attached to CH3C, CH3 group, and O gets converted to OH. So because there are two OH, it is a diol. This kind of a product is also known as pinacol. Symmetrical diols are formed. For example, this one is 2,3-dimethyl butane 2,3-diol. It's a pinacol. So aldehydes do not give this reaction, reduction to pinacols. Only ketone give this reaction. That's all in today's video. If you like the video, please do share and subscribe. Thank you. Have a nice day.